So I'm going to continue the notes that we started in class. If you were not here for the beginning of these notes, we did part 1 together. So it's using the Rice tables that we looked at before. We're given the equilibrium constant for the reaction, and so we're kind of working backwards to see what the concentrations are for our chemicals. So as this says, calculate the equilibrium concentrations for each chemical if a sample of NH4SH is allowed to decompose and reach equilibrium. So the first thing we actually do is, because this is a solid and it's not included in the Kc expression at all, we go ahead and just cross it out because it doesn't affect our reaction. On the other side, we can go ahead and say that our products are both 0 for initial concentrations. It doesn't say that, but it says that this chemical is just decomposing and hasn't decomposed yet, so they're going to start at 0. Now, the information given doesn't tell us enough to actually put in values for any of this, so we use x, a variable, to help us out. So we know that we're starting with 0 of this chemical. We have to add to it. We can't subtract from 0 and get a negative molarity. It doesn't work that way. So we have to add. We're going to add x, or 1x, because this is a coefficient of 1 and we want to incorporate that mole ratio. So we're going to add x. This is also a coefficient of 1, so we're going to add x. So 0 plus x is x. Same thing here. And as always, we then take those values and we plug them into the equilibrium expression. So we did that. Our Kc value was given, so we plug that in here. Ignore the red for now. So we plug that in. These two values from our expression end up being x. So we put x times x, so x squared. Now to simplify this and solve for x, we had to take the square root of both sides, and we got that x equals 0.011. To record and report the final answer, we have to actually state what the concentrations of each of the chemicals are. They are equal to x in both of these cases, but that's not always true, so we want to make sure we actually record the values. So the concentration of NH3 ammonia is 0.11 or 0.11 molar. We want to include that units because it's a concentration. And the concentration of H2S is 0.011 molar. So we did this one together in class. And the second one is very similar to it. So take a look at this one. Some classes got to this, but not all. So this second one, we have that calcium sulfate dissolves with a KSP of 2.4 times 10 to the negative 5. So we're given our K value again. It says determine the equilibrium concentration, so we're looking for these, of each ion if excess calcium sulfate is dissolved to create a standard solution. So we're dissolving our calcium sulfate to create this aqueous solution of these two ions. Now again, this one is a solid. It's not included in the expression, so we can go ahead and cross it out. Again, we are dissolving this, so we're starting out with 0 products, and we want to go from there. We want to add to this side because we are starting with 0. We don't know how much we're adding because this information doesn't give us anything. So we're going to add x. This is going to be 1x because its coefficient is 1. And this is going to be 1x because its coefficient is 1. And we'll take a look at the next one, the next example with different coefficients. So we have 0 plus x is x, 0 plus x is x, and now we want to plug in to our equilibrium expression. So we've got KSP. This stands for solubility product, SP. It's just basically dealing with things dissolving. And it's going to have the concentration of calcium ion times the concentration of sulfate ion. This one does not have a denominator because we are dealing with a solid. It's not included. So we can plug in 2.4 times 10 to the negative 5th equals the concentration of calcium in equilibrium is x, and sulfate is x, and x times x will give us x squared. From here, we want to solve for x. We're going to take the square root of both sides of the equation, and x will equal square root of 2.4 times 10 to the negative 5. 0.00489. I'm going to go ahead and put that in scientific notation. So 4.89, we have two significant figures, so 4.9 times 10 to the negative 3. That's our x value. So again, we want to report our final concentrations of these two chemicals. A simpler way, if the chemicals are the same concentration, like this first one, another way we can report them is to say that calcium 2 plus concentration is equal to the sulfate ion concentration, which is equal to 4.9 times 10 to the negative 3. And again, we're dealing with concentration, so that's going to be units of molarity. Okay? So since these two are the same, they're equal to each other, we can set it all equal to 4.9 times 10 to the negative 3. So this, again, solving for this x piece, when we're not given enough information, but we're given the equilibrium constant, we can kind of work backwards. All right, let's do one that's not coefficients of 1, a little more exciting. So it says, what if the chemicals do not have coefficients of 1? The coefficients must be incorporated into the change in x values. Now, first thing, somehow I ended up with this first line from a different problem that is not supposed to be there. Just cross that out. Now, it says a gas chamber initially contains, important stuff, 1 atmosphere of nitrogen and 1 atmosphere of oxygen gas. If the equilibrium constant, Kp, for the reaction is 4.16 times 10 to the negative 4, determine the partial pressure of each gas at equilibrium. Now remember, when it says partial pressure, that's what's the pressure of each gas. Okay. So we are given some more information than the last questions. There aren't any solids or liquids, so we can't cross anything out. But it says we have initially has 1 atmosphere of nitrogen and 1 atmosphere of oxygen. So those are the only thing that are put in there. So that means our NO is 0 atmospheres to start off as. Now, we don't know how much is changing. We don't know, doesn't give us any sort of change or equilibrium values. So again, we're going to use X. Since we're starting with our reactants and no product, we have to form some products. So we have to add on the product side. That means we have to subtract on the reactant side. Now we're going to use X as our variable again. So we have a coefficient of 1 on N2, so it's just X. Coefficient of 1 on oxygen, so it's just X. But we have a coefficient of 2 on NO, so we're going to put 2X for this one. So you just make your X value match your coefficient. All right, and now we want to do our math. So we have 1 minus X. We can't solve that, so it's just 1.0 minus X. Here, again, 1.0 minus X. And then here we have 2X. 0 plus 2X. So we have some values. We want to plug them into our expression. So we have Kp equals, since it's in terms of pressure, we want to write these as partial pressures. So our product's pressure of NO, and it's going to be squared, divided by our reactants. Pressure of N2 and pressure of O2. And we want to plug in. So we've got our Kp value, 4.16 times 10 to the negative 4 equals our pressure of NO is 2x and it's squared. I'm going to go ahead and leave it as 2x and not square it yet, and you'll see why. And on the bottom, we have 1 minus x and 1 minus x, and they're being multiplied. So we have the same value being multiplied by itself, so we're just going to square the bottom. Now remember, in our previous ones, we just had x squared on the right. We square rooted both sides. Well, we have something squared on the right side. We can still take a square root of both sides. And all this square root will do is get rid of these squares. We have to do it on both sides. So on the left side, we have 4.16, 10 to the negative 4. Oh, I didn't square root it. There we go. And I'm going to go ahead and put it in regular notation just because it'll make our math a little easier to deal with. So we get 0.0204. Okay. And we took the square root of that. So that gets rid of this square and that square. It leaves our 2x over our 1.0 minus x. So we have this kind of awkward algebra problem. A lot of people remember, and it helps them out when they put both sides into a fraction, and then we're going to basically cross multiply. So we get the 0.0204 times 1 minus x. So the 0.0204 times 1, I'm just going to bring it up here, is 0.0204. And then that same number times the negative x, we're going to get negative 0.0204x. And the 2x times 1 is equal to 2x. Okay, so we've got that part. Now we need to gather our like terms. I'm just going to keep switching off colors so you can track what I'm doing. So we want to get our x's together, so we're going to add the 0.0204x to both sides. No, I meant to put a plus sign there. All right. So we have 0.0204 and 2.0204x. And we want to solve for x, so we need to divide by its coefficient. I think a couple classes we stopped right there. So we get x equals 0.0204 divided by 2.0204 gives us 0.0. Let's see, we have, our givens had 2 significant figures and 3 there. We're going to go with 2. Just 1 0. All right, that's all we get. So that is our x value. Now, as we did before, we're not done. We want to report what these actual concentrations are, because they're not just x. This is 1 minus x, 1 minus x, and 2x. So I'm going to scooch it in up here because I ran out of space a little bit. So our concentration of N2 is equal to the concentration of O2. They're the same. And they are going to be 1 minus our answer here, 0.01. 0.99 molar. And there, oh, these are gases. This was atmospheres. Whoop. Fix that. And our last one, our concentration of NO, it's not the same as the other ones because it's 2 times x. So 0.01 times 2 is 0.02 atmospheres. And that would be our final answer. So this one's a little more complex because we're not given nice just 2x and we can square, or x squared and we can square root it. We have a little more calculating, but it's all basic algebra. There is the possibility that they can get more complex than this, but that uses quadratic formulas and they don't do those on your AP exam, so it saves us time. Let's try our last one here. Gives us our reaction. It says, suppose for a synthesis of hydrogen fluoride, so we're making hydrogen fluoride from hydrogen and fluorine, 6.000 moles of hydrogen and 6.000 moles of fluorine are mixed in a 3-liter vessel or flask. Assume the equilibrium constant for the synthesis reaction at room temperature is 1.5 times 10 to the second. Calculate the equilibrium concentrations of each chemical in the flask. All right. So, very similar setup here. The biggest thing is that we are given moles of each of these and then liters. And there's a couple in the other worksheet that did this. Whenever we're given that, we can go ahead and just divide them and get our molarity of each. Now, since it's 6 moles divided by 3 liters, that gives us 6 over 3 is 2. So it gives us a 2 molar solution for both of our chemicals. So we've got H2 gas plus F2 gas in equilibrium, this should be both directions, with 2HF. So rice equal. All right. So let's start out. We are given the moles of hydrogen and fluorine. We said they were both 2 molar. We got 4 sig figs and 4, so we're going to keep all 4. We don't start out with any HF because it says just those 2 are mixed in the flask. And then we're not given anything else besides our equilibrium constant. So similar to our previous one. So as always, we want to add on the right side for this one because it starts as 0. We have to add to that. We want to subtract on the left side. And we don't know what our values are. We aren't given that information, so we're going to use x. So x here, because it's a coefficient of 1. X here, coefficient of 1. And 2x here. So we're going to have 2.000 minus x, 2.000 minus x, and 2x. So you can see that when we get these setups like this, it's going to end up being calculated very similar to this other one. If you want, it'd be a good idea to pause the video here and try the rest of this one out, see if you can set it up, and then come back and check. Alright, I'm going to keep going. Let's see, I'm going to do it over here. So we've got our Kc expression. We want our products over reactants, so concentration of HF squared over H2, and F2. There we go. We want to plug in. So we are going to have our Kc value 1.15 times 10 to the second equals HF squared. HF is 2x and it's squared. And on the bottom, or H2 times F2, and they're the same. So they are squared as well. So, just like we did in the last one, we're going to take the square root of both sides. So we get 2x over 2.000 minus x. And that is 1.15 times 10 to the second. Oop. Insert square root. There we go. 10.72. So we do have 3 sig figs on that. So 10.7. Alright. So now we want to, like we did in the last one, we want to cross multiply. So we have 10.7 times 2, which gives us 21.4. And then 10.7 times negative x, so minus 10.7x equals 2x times 1, 2x. We want to get our x's on the same side, so add 10.7x, both sides. 21.4 equals 12.7x. Divide each side by 12.7. And x is going to equal 21.4 divided by 12.7. 685. We have 3 sig figs, so 69 is our x value. Alright. So now that we have that, again, we can't just leave it at x. We have to plug back in. So we have 2.000 minus x. So 2 minus, our x is 1.69. So we get that hydrogen, and it's the same as fluorine, equal to 0.31. And it is concentration, so molarity. You guys can't see all that. There we go. And our HF is 2 times x. So we have 2 times 1.69, our x value. and we get 3.38 molar. All right. So using these rice tables, it's very similar in terms of our setup. We're just trying to fill in as much information as we can. It's just that we get stuck when we don't have as much information and we have to use X as our variable. But we're also given that K value, so it can have us, it can allow us to solve for X. I hope this helps. You guys have the other practice, and remember that I did mess up, so the practice on this goes 1 through 6 on the back of that one, and then, can't look at my answers. Covered it up. We attached 7 and 8 from worksheet 1, so that, because they were attached to the wrong worksheet. So some of you guys already tried these out and solved them, so that's awesome. All right, thanks guys.